Okay, round 2, section 2.5. For you, this is the first time you're seeing it. For me, this is the second time I'm talking about it. So let's get started. Solutions by substitutions. So normally, we can solve a differential equation by recognizing its type. So the types we've seen so far are separable equations, which you solve by separating and integrating, linear equations, which you solve via the integrating factor, and exact equations, which you solve by whatever you call the exact stuff. This is how we normally solve a differential equation. We see it, we know how to solve it, we do it. But what if you get a differential equation that doesn't fit into one of our archetypes, right? It's not separable, it's not linear, it's not exact. What can you do? Well, you can sometimes, if you're lucky, use a substitution. This is a lot like a U substitution, right? In a U substitution, in integral calculus, for example, you say U equals like something complicated, right? And then the resulting integral in terms of U is easier, right? So you substitute something complicated for U, which is something easier. And that's the same idea with the substitution and differential equation setting. We're going to have some complicated expression that we're going to substitute out and have a new differential equation that's simpler to look at and solve. This is often the first step when you're tackling these difficult equations. So let's say we have a differential equation, first order differential equation that looks like this. dy dx equals some function of x and y. You can substitute out the y, right? You can substitute out the y by plugging in a function of x and some unknown variable u, right? This is just like a u sub, where u is some function of x, right? So you're basically saying, okay, let's let y be some function g of x and some other function of x, right? You're saying let's let y be a function of x and some other function of x. And in that case, it might simplify both sides of the differential equation. If g has continuous first partials, then by the chain rule, the derivative of y, right, partial x, is going to be partial g, partial x. And since this has continuous derivatives in both x and u, then the derivative of y with respect to x is, this is the chain rule, right? This is the chain rule. Derivative of the outside times derivative of the inside plus derivative of the outside times derivative of the inside, right? And since dx is 1, right? This becomes a 1. We can write dy dx after the substitution, right? After the substitution, y equals this. We can write dy dx equals g sub x plus g sub u du dx. So this is like, you know, you pick your u, right? Pick your u equals something in integral calculus, right? You pick your u, and then the next step is you need to calculate what du equals, right? That's kind of the idea here. We're picking our u equals something, and then we're calculating du in order to do the substitution. So going back to the differential equation that we started with, let's substitute in y equals g of x and u, which is a function of x, right, into this equation. So this is our old equation. Now, we know from our previous work, right, that dy dx becomes this creature on the right-hand side. So dy dx becomes this creature. And f, we just substitute out the y for g, right? We just substitute out the y for g. So this is our new differential equation. And if we do a little rearranging, basically we're going to solve for du dx, right? You move this term across the equal sign, and then you divide both sides by g sub u of x and u, right? And that gives you du dx by itself on the left, and on the right hand side is some complicated expression, right, which you could write out. This is like little f minus g sub x over g sub u, right? That's what's on the right hand side, but it doesn't really matter, right? What matters is you have a new first order differential equation. You started with dy dx equals f of x and y, and you ended with du dx equals f of x and u. So you've essentially substituted u for y, right? This is substitution. And in general, it's pretty hard to know what to do. But there are some specific cases that are easier to recognize, right? So there's a chance that you can now solve this resulting differential equation for u, which is some function of x. And if you can, then the solution to the original differential equation can be found by plugging in this phi of x into the expression for y, right? So if you can solve this equation for u equal to phi of x, right? Then you can take that solution and plug it in. Oops. I don't have the expression for y. But you can plug it into the y expression to get a solution to the original differential equation. That's kind of the idea. Okay, let's talk about homogeneous equations. So this is a special type of equation. A function itself, right, a function f is homogeneous of degree alpha if when you plug in f of tx and ty, you get t to the alpha times f of x and y, right? When you plug in tx for x and ty for y, you get out the end t to the alpha times the original function of x and y. This is called homogeneous of degree alpha, right? Here's an example. This function fx of y of x to the fourth, y to the fourth is homogeneous of degree 4. Why? If you plug in tx and ty instead of x and y, right? Plug in tx and ty in for x and y, then this evaluates to tx to the fourth, ty to the fourth, which is t to the fourth x to the fourth, t to the fourth y to the fourth, and you can factor out a t to the fourth from both terms, right? Factor that out. You get t to the fourth times x to the fourth, y to the fourth, and this term here is this term here, which is f of x and y. So f of tx, ty is t to the fourth times fxy, which means this is homogeneous of degree 4. Here's another one. fxy equals square root of x, square root of y is homogeneous of degree 1. Since plugging in tx and ty, you get tx to the 1/2, ty to the 1/2, which is t, x to the 1/2, y to the 1/2, which is t times f. So this is homogeneous of degree 1. These are very special functions, by the way. In economics and business applications, these homogeneous functions show up a lot in terms of like production functions. Because in economics, when you scale up the, like, let's say capital and labor inputs, then it should scale the function. Sorry. It should scale the output by, okay, you get what I'm saying, I think. These show up a lot in economics and business situations when you're looking at production functions, these homogeneous functions. So a shortcut here is a function will be homogeneous if each term has the same like total degree, right? What do I mean by that? If we look here, right, the total degree of this term is like 1/2 plus 1/2. You add up, every time there's a plus sign, you take a term and you add up all the exponents in that term, right? So if we look up here, right, this function has 2 terms, right? 2 terms separated by a plus sign, and the total degree over here is 4, and the total degree over here is 4, which makes this homogeneous of degree 4, right? This has 1 term, so it's automatically homogeneous. Here's a definition for you. A differential equation that looks exact, right, but not necessarily exact, but a differential equation in the differential form is said to be a homogeneous differential equation if both m and n are homogeneous functions of the same exact degree, right? So if m and n are homogeneous functions of the same degree, this differential equation in its differential form is called a homogeneous differential equation. Now, if your differential equation is homogeneous, we can use a clever little substitution, u equals y over x or y equals u times x, to obtain dy equals u dx plus x du. Right? So we can replace the dy term right here, right, with dx, u dx plus x du. So if this is a homogeneous differential equation, you can do this clever little substitution, which gives you this dy, and plug that in right here. So now our, this is our OG equation, right? Original equation was m of x and y dx plus n of x and y dy equals 0. This was a homogeneous differential equation, right? Now when we make the substitution, y equals u times x, right? We're going to make the substitution y equals u times x. We also got to make the substitution dy equals u dx plus x du. All right, so that's what we're going to do. The y becomes ux, and the dy becomes u dx plus x du. And this comes from the chain rule, I should say. This right here. This comes from the chain rule. All right, I guess I should say the product rule, not the chain rule. Product rule. Right, the product rule. Okay, but what do we know? We know that m is a homogeneous equation. And we know that n is a homogeneous function, and they have the same degree alpha, right? And since this is equal to m of x times 1 and then x times u, we know we can pull this factor of x out front, right? Since this is homogeneous, this m is a homogeneous function of degree alpha, we can slide these x's out front and we pick up an x to the alpha out front, right? That's the definition of being a homogeneous function. And since these are both homogeneous of the same degree, we get the same x to the alpha out front on both terms, right? So now my equation becomes x to the alpha m of 1 and u, right? Because the x's got pulled out front. The x's got slid out front, dx, plus x to the alpha n of 1 and u, because the x's again came out front, times u dx plus x du equals 0. And since this side is equal to 0, I can cancel these x to the alphas on both terms. So now I'm going to collect up terms. I want all my dx terms to be together, and then I want my du term to be on the other. I want it to be something dx, something du, just like an exact equation would look. Something dx, something du. Okay, what are my dx terms, right? I've got an m dx and I've got a un dx. So I've got an m dx and a un dx. And then du, I've got an x times n du. Now, what's magical here is this will always be a separable equation, right? So we started with something that looked exact, we make the substitution y equals u times x, right? Y equals u times x, and it turns into a separable equation. Okay. Because this is all in terms of u's, this is all in terms of x is in u. We'll just see how it goes. Let's do an example. Let's solve this differential equation. Now, this is not exact because if you check, right, if you check the derivative here, if you check m sub y, you get 2y. And if you check over here, n sub x, you get 2x minus y. These are not equal to each other, right? These are not equal to one another, which means it's not exact. But both m and n are homogeneous of degree 2, right? And we can see that by calculating the total degree of each term, right? This m has two terms. Total degree 2, total degree 2. This is homogeneous of degree 2. In terms of n, we also have two terms. The total degree here is 2, and the total degree here is 1 plus 1, which is 2. So since all terms in both equations, or in both functions, have total degree 2, this is a homogeneous. These are both homogeneous of the same degree. Now, since they're homogeneous of the same exact degree, I can use this substitution, y equals u times x. And then again, dy equals x du plus u dx. And when you plug in y equals u times x and dy equals x du plus u dx into these fine places, what do you get? Well, you get x squared plus u squared x squared here, dx. You get x squared minus ux squared here. And then the dy becomes u dx plus x du. And now, since these were both homogeneous to start with, I should be able to factor out all of the x's. Right? So all the x's come out here, all the x's come out here, and we can see that it does indeed work. We get an x squared, we get an x squared. I mean, technically you can cancel these, but it doesn't matter, I think, one way or the other. I guess I should have, but it's okay. So now I'm going to gather up my dx terms, and I'm going to gather up my du terms. So my dx terms, right, there's this term, x squared 1 plus u squared, and then there's this term, which is x squared u 1 minus u, all times dx. And then my du term is x cubed 1 minus u du. And if you were to combine terms over here, what would you get? You'd get x squared plus, what is this? This is x squared. I can factor out an x squared from both terms. And I'm left with a 1 plus u squared minus u squared, which is equal to x squared times 1 this is supposed to be a plus u, 1 plus u. That's how I got here. All right, this whole term simplifies down to this. And then over here I have x cubed 1 minus u du. And this doesn't look it at the moment, but it is separable, right? It is separable. And you can put all of the x's on one side and all of the u's on the other side. And here's how it looks. I divide everywhere by x cubed. And I divide everywhere by 1 plus u. Right? 1 plus u cancels, the x cubed cancels. I'm left with 1x in the bottom down here. And I get 1 over x dx plus 1 minus u over 1 plus u du equals 0. And now if I integrate both sides, right? Integrate both sides. I get this step, and unfortunately I'm going to have to do some long division here. If you don't remember polynomial long division, right? Polynomial long division. Now's a good time to go refresh your memory. In order to divide 1 minus u by 1 plus u, right? I stick 1 plus, or really it's u plus 1. I put u plus 1 in the bottom, and then I put minus u plus 1 in the inside the house, right? The top guy makes it inside the house first. The guy on top makes it inside the house first. U times what is negative u, negative 1, multiply that, remainder of 2. So that means this equals 1 plus 2 over 1 plus u. Sorry, negative 1 plus 2 over 1 plus u. That's the long division. Okay, which means this is my integral. Now I can calculate this, pretty straightforward. Integral of 1 over x is natural log absolute value x. Integral of negative 1 is negative u. Integral of 2 over 1 plus u is 2 natural log absolute value 1 plus u. Plus a friendly constant equals 0. Now, I go back, right? I go back, I unsub u back for y over x. And after some cleaning up, this is just algebra. And then this is just algebra, right? And then this is just algebra. I get a solution, right? Solution to the OG differential equation. A solution to the original differential equation. Okay, and then here's the next type. Bernoulli equations. Sometimes we have very special differential equations that almost look linear, right? They almost look linear. They've got the dy dx by itself. They've got the pxy. But then they've got fx times y to the n, right? So this is a nonlinear term. Nonlinear term. How do we deal with this? Well, if it's exactly in this form, this is called a Bernoulli equation. And when you know it, there's an easy way to solve these in general. So if n is equal to 0 or 1, right, if this exponent on y to the n is 0 or 1, then the equation is actually linear, right? If it's not 0 or 1, but it's some real number, then you can use the substitution u equals y to the 1 minus n. Right, u equals y to the 1 minus n. We'll make the equation be a linear equation. Here's an example for you. X dy dx plus y equals x squared times y squared. If I divide by this x out front, right, divide by the x out front, I get dy dx plus 1 over yx plus equals xy squared. Now, this is not linear, right? Not linear. But it is Bernoulli. It's Bernoulli with n equals 2, right? Bernoulli with n equals 2. So in that case, I'm going to use the substitution u equals y to the 1 minus 2. Right? Bernoulli with n equals 2. I use the substitution u equals y to the 1 minus 2. Which means u equals y to the negative first power. Which implies that y equals u to the negative first power. Now that I have this expression for y, I can go back to my differential equation and plug in, right? Plug in for y everywhere. Plug in for y everywhere. So I get dy dx, right? Dy dx equals, there's no x's. The derivative of y with respect to x is negative u to the minus 2 times du over dx. Right, because remember we're still treating u like a function of x. right? This is like u like a function of x. So that means dy dx equals negative u squared du dx. And when I substitute, right, dy dx becomes negative u to the negative 2 du dx. 1 over xy becomes 1 over x u to the minus 1, because that's what y is equal to. And x times y squared becomes x times u to the negative 2 power. And now I'm just going to go through and divide everywhere by negative u to the negative 2. Right? That cancels here, that cancels here, and then this and this cancel, and we're left with a u by itself here. So I get du dx minus 1 over x u equals negative x. This is now linear with p of x equal to negative 1 over x. Right, this is my p of x, which means I can solve this via the integrating factor. I can solve this via the integrating factor. And in that case, the integrating factor is e to the integral of p dx, which is e to the integral negative 1 over x dx. And when I integrate this, I get e to the negative natural log absolute value x. And I can move this negative 1 up to the exponent, right? I can move this negative 1 up to the exponent and get natural log absolute value 1 over x. The e and the natural log cancel, and I get 1 over x, right? And obviously I'm choosing an interval here of definition. Which means, now that I have my integrating factor, I know that this equation is going to become d dx of integrating factor times u equals q times integrating factor. Right? This is how we solve. This is how you solve linear equations. Which means integrating both sides, right? Integrating both sides gets rid of that. 1 over x times u equals negative x. This becomes negative 1, I should say. Right? Integrating negative 1 is negative x plus c, which means multiplying everywhere by x to cancel this out. U equals a negative x squared plus cx. And then one last step, going back to y, right? You have to go back to y. That means y to the negative 1 equals this, which means y equals this on this interval. This is a solution to the OG differential equation. And last but not least, if dy dx equals some function of ax, by, and c, then you can substitute u for this linear term, given that b is non-zero. And that makes the differential equation separable. Let's see how it works. dy dx equals some linear function of x and y, right? This whole thing is f, and we can view f as a function of negative 2x plus y, right? We can view this as a function of negative 2x plus y, just like what's written up here. And in that case, if we let u be this complicated thing, then y is this, which means dy is two dx plus 1 du dx, which is 2 plus du dx. And after substituting in, we get dy dx equals this, and u equals this. Which means, by moving this across, du dx equals u squared minus 9. And when you know it, this is separable, right? This is separable. It's stuff times 1, right? Times 1 on the right-hand side. So by dividing both sides by u squared minus 9 and multiplying both sides by dx, I get 1 over u squared minus 9 du equals dx. To solve this, you need to use partial fractions again. So this is partial fractions. Partial fractional decomposition says that the factors of this are u squared minus 9 equals u minus 3 times u plus 3. Right? So I'm going to split it up into u minus 3 and u plus 3. And these are the a and b you get on top. And now this is easy to integrate. Right? Integrate both sides. I get 1/6 natural log of u minus 3 minus 1/6 natural log of u plus 3. Integral over here is x plus c. And by using the powers of logarithm rules, subtraction outside the log becomes division inside the log. So I get 1/6 out front, and then I get natural log of u minus 3 over u plus 3 equals x plus c. And then I just need to multiply through everywhere by 6, multiply by 6, multiply by 6. That'll cancel out this 1/6. And just like we've seen before, raising both sides to the e, right? You can break off this e to the 6x, e to the 6c, and that becomes e to the 6x times like a constant, just another constant. So that's what happened here. Or, so this is just me multiplying things across and solving for u. Which means now I can go back to y, right? Remember that u was equal to negative 2x plus y. So y minus 2x equals this. And since y of 0 equals 0, that means c equals negative 1, which means this is my solution. Solution to the differential equation. Okay. I hope that wasn't too bad. It's a little annoying to remember, but there's only 3 types of equations that I could ask you about, right? There's only 3 things I could ask of you. Either I'm going to show you on the test a homogeneous exact, well, not really exact, a homogeneous equation which is in differential form, right? In which case, as long as it's homogeneous on both parts, you can use this every time. Or you're going to see a Bernoulli equation, in which case this is the substitution you use every time. Or, last case, you see a function of something complicated and you just do what your gut tells you, right? Like, if you were in Calculus 2 and you saw this, your gut would say, make this be u, right? And that's basically what you do in the last type. This is every time. So really, there's only 3 possibilities for what I could ask you to do on the test. And all 3 of those have a specific form that they always follow, right? A specific form that they always follow. Okay.